All right, so we have 50 minutes, so let me start out with a review of what we covered last time. So we covered the double-slit interference. So I'll try to time myself to this in 5 minutes. So with the double-slit interference, this is what we covered. We were looking at the situation. So if you want a picture, there's a picture of the experiment. Would be something like this. In our experiment, we are using laser instead of single slit for this, so it's a lot easier for us. So experiment is set up like this with two slits separated by some distance d, and you get this interference pattern that you have seen in previous lecture. So let me just quickly go over what we talked about last time. So we are analyzing a situation where light rays are coming through two slits separated by distance d. So some light rays come through, shine through these two slits, and we are imagining a screen that's very far away. And when we look at the light, the path to the screen that's very far away, those paths will be more or less parallel. So the key thing in analyzing this was looking at the path length difference between these two paths from two slits. And this is the geometry that you have seen last time. Sorry, wrong color. So it's this path length difference that we used to help us analyze when are we going to get constructive interference, when are we going to get destructive interference. So as you recall, this path length difference turns into phase difference. And phase is going to be the key idea as we go through the rest of interference and diffraction for the rest of the next week. This turns into the phase difference of 2 pi times the path length difference divided by the wavelength. And depending on whether this phase difference is 0, 2 pi, 4 pi, even the integral multiples of a cycle, or whether it's a half a cycle, you get constructive interference or destructive interference. So the relationship that we derived the last time was for constructive interference, or this would be the bright fringes that you see. You have this condition that has to hold, that this separation between the slits times sine of the angle theta, that would be this angle theta, is equal to some integer multiple. I used n last time, but it looks like everyone else is using m, so let me use m. M times lambda, where this m is an integer. So m goes from 0, plus minus 1, plus minus 2, and so on. And last time we saw for destructive interference, this would be the dark fringes that you see. So similar condition, except instead of one integral cycle, we are looking for half a cycle. So one way to express that would be the sine theta, that's the, some cycle difference is equal to, and so still integer, and I think I want this to be minus 1/2 times lambda. I mean, it could have been plus, it could have been minus, but making this minus makes it easier for counting what we are going to call order for your homework problems and for the lab. So here, m equals 0 is a little bit iffy, so let me just say m goes from 1 to 3, and so on. And I guess if I want to put minus sign, I would put plus minus here, but let me not bother with that. Usually when we say a positive angle, there's something similar on the symmetric other side. Okay? And these numbers are what we refer to as orders. First order, second order. 0th order is the central maximum. We don't really say 0th order. Let's see, okay, almost out of the 5 minutes. So this is what we talked about for double-slit interference. And I just want to remind you of a mathematical tool that we spent a fair amount of time introducing last time, because the whole reason I did that was to be able to use it today. And today is going to go much quicker thanks to spending that hour last Tuesday. So this is the simple mathematics, and what we want to be able to analyze is for intensity of light in double-slit interference. And I showed you how to do it using the real functions of sines and cosines, and starting out with, starting from the description of electric field as a function of, I guess, well, as a function of position and time, where y is position on screen, and time, and E naught cosine omega t plus the phase factor, which would depend on position. Like, we've went through all this. You've seen how long it took. And after having done that, what we took even more time going over is this new mathematical formalism. That is a bit out of sequence for this class. But unlike in physics 4b, where it was totally out of sequence, here it's something you are going to need when we do quantum mechanics. So I'm just bringing it a little bit earlier in the semester than later. So that little bit that I'm writing here as a reminder is complex functions to represent, I guess, cosines and sines, to represent cosine and sine. So for example, if you have a function that looks like this, some function of time, it could be position too, but some function of something looks like some amplitude times cosine of omega t plus phi, then what we are going to, what I did last time and what we are going to continue to do today is we are going to introduce a related complex function. A related complex function with this squiggly line reminding me that it's complex. That looks like amplitude times exponential of the complex exponential of I omega t plus phi. And my justification for doing this earlier is that it's something you're supposed to know from trigonometry, because this is coming from e to the Euler's formula. E to the I theta is equal to cosine theta plus I sine theta. And so this is what we are going to use to represent this periodic function. And there are several advantages in doing that. One is here. The phase factor is inside the cosine. It's mathematically a nightmare to deal with. But once you express it with an exponential, you use some exponential algebra to actually separate it out as a factor. So it's e to the I omega t, and there's a e to the I phi. Using exponential algebra, it becomes the first exponential times e to the I phi. So this will make mathematical manipulations much easier and allow us to do some things that your textbook does more complicatedly. Let's see. And whenever you want to go back, let's say you start using complex function, and if let's say you don't like it, you can always go back by taking the real part. And in between these two, I gave you one thing to be careful about. So let me express it this way. I can describe it in terms of allowed operations and disallowed operations. So for example, with this intention of taking the real part in the end, if you do these are perfectly fine. So if you have some function, real function f plus some real function g, then you can totally represent that with complex function f, the complex version, plus complex function g, and you take the real part, you'll go back to the originally what it was. And in fact, it works for minus as well. Subtraction is just adding a inverted version. And you can also, that's one set, and you can also multiply by any scalar. So if you have some function here, and let's say you are multiplying with some real number, then you can do the exact same thing in the complex representation. And actually, in the complex representation, there's one more thing you can do. If you multiply by a complex number, you can use that to shift the phase of the function. But let's not do that. What is not allowed, and what you have to be careful with, is any kind of multiplication. So if you had a function that looked like this, f times g, and if you were to do similar operation here, take the complex representation, multiply with the complex representation of another function, and if you were to try to do what I was telling you you could do, just to take the real part, then this would not work. You would not get the result you were expecting to get. And we went over last time how it's because in the multiplication, you mix in some of the imaginary parts, so the relationships you are relying on doesn't work anymore. But one thing that's useful to have as a special case is this thing that we went over last time that I'm going to use today. And I presented it without a proof, and some of you are asking about it after class. And I remember seeing a proof at some point, and I'm just going to leave with it a special formula that's useful for you to know. So let me just write it down as a special case. So this works when, let's say you want to calculate this. You want to take a function, which is a function of time, and for whatever reason, you are not interested in the function itself, you are interested in the square of that function. So you are going to take the square of this real function, and in fact, you are not even interested in the square itself, you are interested in the time average of this. So let's average it over some time. So integrate it with respect to t from 0 to some time t, and then divide by 1 over t. This is the time average. And the special case is this. This can be represented by an expression that doesn't involve any integral at all with the complex representation. The complex representation being take the complex function, multiply by its complex conjugate, and I think if you are being perfectly correct, you have to divide it by 2. This is the special case that I brought up last time, and you saw an example of that with the double-slit interference. So this is what we did the last time. It took us like 3 minutes to do it last time, so I think it's worth doing it again for 3 minutes. So we want intensity of double-slit interference starting from the representation of the electric field. So when you have double-slit, and you have some screen here, and you have light that's coming from these two slits. So you are looking at a particular point on the screen with there's light coming from one slit or the other slit, and both of those can be represented with this function. But you can describe them by describing their electric field of that light. So this is slit number 1 and 2. So electric field of slit due to 1. So before I would have written this, now I'm going to use the complex representation. So the complex representation is E naught times e to the I omega t times e to the I phi 1. That's the phase shift phase of the light coming from slit 1. And last time we just left it there because the actual expression for the phase is a little bit complicated. Same thing for the second one. Electric field from slit number 2 comes from E naught times e to the I omega t times e to the I phi 2. So how do we find the intensity here due to light from both of the slits? What principle can we use to help us calculate that?
Superposition and then square.
Okay, superposition and then square. Superposition, because if we want the intensity, this is what we remember. Intensity is proportional to electric field squared. That's the relationship we remember. So we first need total electric field here. That we use the superposition principle. So to get that, we use the superposition principle, by which we mean we just add them together. So the total electric field is just a simple sum of these two. So let me do some simple factoring to save on writing. I've written this last time already. So I'll factor these two common terms, E naught e to the I omega t times e to the I phi 1 plus e to the I phi 2. You can already see, like I couldn't have factored this out if I was using cosine and sine. And to get the intensity, I need to, so with the real functions, what I would have done is I would have squared this and then done the time average. Now what I'm going to do is I'm just going to use this special case to just to multiply this with its complex conjugate and trust that that will represent the time averaged quantity. So let's write that out. So the total intensity that will be averaged in time is the total electric field times its complex conjugate. Some of you here weren't here last time. So let me write out what the complex conjugate is. It's, so E total, it's just that, E naught e to the I omega t times e to the I phi 1 plus e to the I phi 2. And all that's meant by complex conjugate is you, wherever you see I, and you replace it with a minus I. As long as you are sure that none of the letters represent, all the letters are real numbers, which they are here. So the complex conjugate here is E naught, which I'm going to say it's real, times e to the minus I omega t times e to the minus I phi 1 plus e to the minus I phi 2. All right, let me do some of the simpler simplifications before I go further. So E naught, same E naught, so let's say it's squared and get rid of this. E to the I omega t cancel out by e to the minus I omega t. So these two are gone. So I have to do this product a little bit more carefully. So let me take the time to do that one term at a time. So I have E naught squared times, let me number them, 1, 2, 3, 4. 1 times 3, that'll give me 1. I phi 1 minus I phi 1, they cancel out. So 1 plus, let me do 2 times 4. That also gives me 1 because they cancel out. Now I'm going to take a little bit more time. E to the I phi 1, so 1 times 4. That's going to give me e to the I phi 1 minus phi 2. So plus e to the I phi 1 minus phi 2 plus the last one, 2 times 3. So it's going to be e to the I phi 2 minus I phi 1. I'm going to choose to express it as e to the minus I phi 1 minus phi 2. Because then I can, oh wait, I haven't written it yet today. Let me, so this is once again a reminder, sorry. Today is a day of a lot of reminders. From this Euler's formula, this is what we wrote down last time. What we wrote down last time is you can express cosine theta and sine theta in terms of the complex exponential. So cosine theta is e to the I theta plus e to the minus I theta over 2. And sine theta is e to the I theta minus e to the minus I theta over 2I. Right? Yes? So from this, we recognize this as being e to the I theta plus e to the minus I theta. So this is the same thing as this cosine theta here, except double because I don't have that too. So let me write out the final version. the final version of this expression for intensity is E naught squared times 2 plus 1 plus 1. And this is 2 cosine of phi1 minus phi2. And this is the same expression that you have in the textbook once you plug in what the phase difference is. Okay? So, all right, I still have enough time to do the rest of the topics today. So it wasn't quite 5 minutes, but